Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. My name is Amy Draves, and I'm delighted to welcome Colin Adams to the Microsoft Research Visiting Speaker Series. He is here to discuss his book, Zombies and Calculus. This is a novel that provides clues on how to manage a zombie apocalypse using math to calculate the best way to survive. Colin is the Thomas T. Reed Professor of Mathematics at Williams College. He was honored with the Hymo Distinguished Teaching Award, which is the highest teaching honor given by the Math Association of America. He is also the author of 6 previous books and the humor columnist for the Mathematical Intelligencer. Please join me in giving him a very warm welcome.
Thank you. Thank you very much. Thank you very much, everybody. Thank you very much for being here. It couldn't have been easy getting here, given all the zombies that are out there right now. So congratulations on still being alive. It took me 7 weeks to get here, 7 grueling weeks. I lost my dog. I lost my best friend. You know how long we've been best friends? We've been best friends for 3 weeks. This whole thing's really changed the nature of relationships, hasn't it? But the loss of life that was caused by my trip here is going to be offset today by the number of people that are going to be saved by what I have to tell you here today, because I am going to tell you how to survive the zombie apocalypse. We are currently living through one of the most horrific periods in the history of humankind. Suddenly makes Paris Hilton seem kind of unimportant, doesn't it? She's gone, by the way. And so it's been a while now. It's been a few years. There are not a lot of us left. We're doing the best we can under the circumstances. I used to be a professor at Williams College in Western Massachusetts, a math professor. Before the zombie apocalypse descended upon the college is gone now. So much for tenure. But on the other hand, a lot of other institutions have disappeared as well. So no more police, no fire department, no hospitals, no super stop and shop, no crossing guards, no cappuccino latte, no more organic kale. It's all gone. This very building that we're in right now, this building used to house one of the most important corporations in America. What is it now? It's just a place to protect yourselves from zombies. It's really sad. Now, some of you may be sitting there saying to yourselves, okay, so this guy has survived this long, but so have we. Why should we listen to him? What does he have to tell us? Why does he know so much? But in fact, it is true that I used to be the advisor on zombie affairs to the president. That's right, the president of New Western Massachusetts. Or at least I was until he was eaten by the vice president. Now, I'm going to tell you how to survive the zombie apocalypse. And the first thing I'm going to explain is a lot of misconceptions that people have about zombies. So let's talk about some misconceptions about zombies, okay? Number 1, they are the dead that have risen. Now, that's just patently false, okay? They are actually people who've been infected by a virus, okay? They get bitten, the virus gets into the bloodstream, goes up through the blood-brain barrier, and then it gets to the brain where it liquefies most of the brain. In fact, all of the higher brain functions, reaching the point where now people devolve into an earlier evolutionary state. The so-called reptile brain is all that's left. And those people then seems as if they are the dead that have risen, but in fact they are not. They are actually functioning beings at that point. Number 2, zombies can live forever without sustenance. Now that also is silly, okay? There are no living creatures that can live forever without sustenance. If it were true that zombies could live forever without sustenance, we'd just take gyms all over the United States, we'd put treadmills in them, we'd put zombies on the treadmills, we'd have volunteers sitting in front of them. I forgot one thing here. And then we could generate as much power as we ever needed, okay? So it's silly. Zombies need sustenance just like everybody else does, okay? Number 3. Zombies can be cured. Now, as I said, the zombie brain has been liquefied, and you cannot cure a zombie. So if you see your mother coming towards you looking like she's just going to give you a big kiss, that's not what's going on, and if you hesitate for a moment, it could be your last moment, okay? Zombies cannot be cured. A lot of people believe that they could. That was the zombie rights movement. They're gone now, okay? There are no zombie rights people left anymore. They shouldn't have opened up the membership to the zombies. Now, I want to talk a little bit about how to survive the zombie apocalypse. Now, I see a few people here who are dressed appropriately. You're dressed appropriately, right? A zombie can't bite through that jacket. That's smart. Things like this are great. Hockey equipment like this. That's loud. Hockey equipment like this, lacrosse equipment like this. Best thing to do is go to the nearest high school. Go in there. It's going to smell pretty bad in the locker room, but look for stuff like this. It's great protection, okay? The other thing you have to worry about, which is very important, is long hair. So if you have long hair, you're running a huge risk. And so I did bring a couple of these along here. Anybody who needs them. Bath caps, okay? Very important. You'll take a bath cap. Here you go. Bath cap. Anyone else want a bath cap? Bath cap. I think you need one. There you go. Okay, number 3. Now this is the thing that's really interesting and maybe one of the most important things to understand about zombies. And that is zombies are not smart. In fact, there are dogs that are smarter than zombies. Now that looks so good. That's perfect. Okay? So some dogs are smarter than zombies, and I'm going to give you an example. This is a dog named Elvis. And Elvis is a dog who belonged to a guy named Tim Pennings, and he wrote this article, Do Dogs Know Calculus, that appeared in the College Math Journal. And this dog loves to fetch. So Elvis just loves to fetch. And Tim Pennings lives right on the shore of Lake Michigan. And so what he would do is he'd get on the shore, and he'd throw a ball into the water, diagonally into the water, and Elvis would take off after it. Now the thing you have to know about Elvis is, here's a picture of what's going on, Elvis can run 7 times as fast on the beach as Elvis can swim in the water. And so what Tim Pennings did is he'd throw the ball in at various diagonals, at various distances, and Elvis would take off. And what was truly remarkable is that Elvis seemed to be able to find that optimal point, the best possible place that you could go into the water to minimize the time that it took him to get to the ball. Now that's something you can figure out with calculus, where that point is. And it was as if Elvis could intuit where that point was. It's kind of an amazing thing. All right? So let's think about what would happen if you did the same thing with a zombie. All right? So here we are on the shore of Lake Michigan. And of course, you know, if you throw a ball in the water, a zombie's not going to go after a ball in the water. Okay, that's not going to work. So we're going to throw in Charlie Sheen. Okay? So we throw in Charlie Sheen. Here's the zombie. And the zombie, what's the zombie going to do? The zombie should go along the shore a certain distance and then cut into the water. But no, every single time the zombie heads straight for Charlie Sheen. No matter how many times you throw him in, same thing happens over and over and over again. Okay? So the zombie always heads for where the person actually is. So I actually have a video of this that I'm going to show you right now. This happened on the campus of Williams College to demonstrate what happens. You see the zombies down front there. Typical zombie behavior. Instead of running across the front and up the stairs like any rational human being would do, they don't have the brains in their head to do it that way. Instead, they have to come straight for me, straight up the chairs. It's going to take them a half hour to get here. It's very sad. Those are Professors Garrity and Morgan from the Williams campus. So I want to show you another incident that occurred actually very early in this whole process on the campus of Williams College, where there was a dean. I was watching from a window up above, and there was a dean trying to escape from a zombie and trying to get to the Bronfman Science Center. So here you see the dean, and here you see the zombie. Now if the zombie were smart, what the zombie would do would be to cut off the dean, because the zombie is actually moving faster than the dean. This happens to be an old dean, not moving very fast, and the zombie is moving faster. And if the zombie went straight for the dean, the zombie would succeed in catching the dean, just like we're going to see right here. So the dean's moving like that, the zombie's moving a little bit faster, and right there you see the zombie catches the dean. All right? But unfortunately, for the zombie's sake, that's not what happens, because the zombie always tries to head for right where the dean is at any given moment. So in other words, its direction vector, the zombie's direction vector, is always headed towards the dean. The dean's direction vector is headed towards the science center, where he's going to get safe. So let's see what happens when the zombie is chasing the dean. And what happens as we go along, the zombie's vector is always pointed straight at the dean, the zombie's arrow, and we go along, and the dean makes it to the science center because of the fact that the zombie's always heading to where he was. Let's watch that in real time. So the dean's trying to get away, the zombie is still moving faster than the dean, but because the zombie is heading for where the dean was, the zombie never succeeds in catching the dean as the dean tries to escape to the Bronfman Science Center. Okay? So we'd like to try to analyze this situation a little bit more carefully. We'd like to figure out what is that curve that the zombie went along as the zombie was trying to chase the dean. So let's take a look at that, and then we can determine, depending on the relative speeds of the zombie and the dean, whether or not the zombie is going to succeed in catching the dean. So we're going to look at this curve right here. We're going to assume that the dean is starting over here a distance of x0 from the zombie. And then the Dean is always headed straight for the Bronfman Science Center, and the zombie is always having its direction vector pointed straight at where the Dean is. Let's move things forward a little bit in time. So we'll call the speed of the Dean S sub D and the speed of the zombie S sub Z. So let's move things forward a little bit in time. So here is the position of the zombie at this particular instant in time where a certain amount of time t has already passed. And you'll notice still the zombie has its direction vector pointed straight at the Dean. We're going to call the coordinates of the zombie x comma y, and that's what we want to determine is what is x comma y as time progresses. So we'll first look at the coordinates of the Dean. You'll notice the x coordinate of the Dean has to stay at x0 because that's a vertical line right there. The y coordinate of the Dean will just be the Dean's speed times the time. That'll give me the y coordinate of the Dean because that's how far the Dean has traveled at any given time t. All right? Let's just compute some of the differences between these coordinates. So down here you'll see the difference in the x coordinates. The zombie's x coordinate was x. The Dean's x coordinate is x0, so that's the difference in the two x coordinates. The difference in the two y coordinates will just be the Dean's y coordinate minus the zombie's y coordinate, s sub d of t minus y. Okay? Now, this particular line that you see right here, you will remember from calculus is what we call the tangent line. Okay, and the tangent line has a slope that is the derivative. So in fact, the derivative dy dx of this particular curve that we see right here is the slope of this particular line right here. But it's something that you learned very early, that slope is always given by taking rise over run. So that says dy dx should be the rise over the run in this particular case, which means dy dx is equal to s sub dt minus y, that's the rise, divided by x0 minus x, that's the run. And this is a differential equation. Okay, and it's a differential equation that if we can solve, we will then know what this curve is. Okay, so this has to be satisfied by the x and the y that occur that give me the coordinates of the zombie. Okay, so let's take a look at that equation. All right, so we're looking at that equation. We'd like to know, if I have an equation of this form, what does y look like? Okay, and I want you all to be thinking in your own head, oh, I kind of think, I bet you I have a guess as to what that's going to be. Okay, so everybody sort of try to think in your head, okay, what's that going to be? And we're going to call q the ratio of the speeds, the speed of the Dean to the speed of the zombie. So the relative speed, so we get some sort of parameter there that we can use. All right, has everybody figured out what they think that looks like? Well, this is it. Anybody come up with that one? It's bad, it's nasty, okay? So this is actually kind of a nasty equation, but it turns out this is the solution to that relatively simple differential equation, assuming that q is the speed of the Dean divided by the speed of the zombie. Okay, so this is kind of ugly. However, we can still use it very effectively to determine when the zombie is going to catch the Dean, given a particular value of that relative speed q. All right, so let's look at that equation. I'll put it at the top there. And you'll notice that capture is going to occur when they have the same x coordinate. The zombie's following the Dean along, but once the zombie has the same x coordinate as the Dean, the zombie will have caught the Dean. So that means capture is going to occur when the x coordinate of the zombie equals x0, which is the x coordinate of the Dean. Now notice what happens when x equals x0. In that case, this term right up here disappears. Okay, that's all zero. So all this big mess here is gone, and all we're left with is this. Okay, so the y-coordinate of capture occurs at q over 1 minus q squared times x0. Okay? So let's take a look at that in various situations to see what that's telling us. So capture is going to occur in this particular situation here. And here we have the situation where we had the Dean starting at x0. And let's first look at the case where q equals a half. So that means the Dean is moving at half the speed of the zombie. When the Dean moves at half the speed of the zombie, plugging q equal to half in here, we get y equals 2/3 of x0. So that means the Dean gets about 2/3 of x0 up this line before the zombie catches him. Okay? Not a good situation. Okay? That's bad. All right? On the other hand, what if q is equal to 3/4? So the Dean is moving at 3/4 of the speed of the zombie. How far does the Dean get? This time the Dean gets to 12/5 of x0. Okay, so the Dean gets quite a bit of a ways up. Okay, so that's not so bad. And in fact, that's far enough to make it to the Bronfman Science Center. So the Dean makes it to safety in the case that the ratio of their speeds is 3/4. So that's good news. Okay, that's great. Okay, what would happen if q equaled 1? So that means the Dean and the zombie are actually going at exactly the same speed. Well, in that case, you'll notice the zombie's always going to be following the Dean. And in fact, in that case, capture never occurs. Y equals infinity. The Dean never gets caught. Okay? Now the bad news is, unfortunately, as I told you, that in fact it was Q equals 3/4, and yes, the dean did make it into the Bronfman Science Center. Unfortunately, the Bronfman Science Center was full of zombies, and it really didn't turn out so well, so that's too bad for the dean. Okay, so now I want to look at a different situation. So this was a situation where I had a zombie chasing someone who was moving in a straight line. But a particular situation that occurred when this all started on the campus at Williams College was a circle pursuit, where I was riding a bike and I was trying to attract zombies away from some other people. And so the situation is this one. I'm riding a bike around in a circle. The zombie is going to chase me, but still the zombie is always going to be headed straight towards where I am. Okay? So the zombie's direction vector, also called the tangent vector to its curve, will always be pointed straight at me. So we want to figure out what that's going to look like. So my coordinate, first of all, we have to figure out. So I'm on a circle of radius capital R. I'm going to call my angular speed omega. So my angle is going to be omega times t at any given time. My x coordinate I'll call x sub a for atoms, y sub a for atoms. And you'll notice that x sub a is just going to be equal to r cosine omega t, basic trigonometry, this divided by this. And y sub a is going to be r sine omega t. Okay? So I can figure out very easily coordinates of my point on a circle as I'm moving around that circle at a given speed. Now, the zombie, so this is now the zombie's coordinates again. The zombie's coordinates, the zombie is moving along a curve. And I'm going to assume that the zombie's coordinates right now are x of t, y of t. Okay, so I have a curve given by x of t, y of t. And if I want to find that direction vector that always has to point towards me, that direction vector is simply going to be the derivative of this particular parametric equations of this curve. So the velocity vector, which is the derivative x prime, y prime, is tangent to the curve, and it has length equal to the speed of the zombie. Okay, so that's the thing that I want to have pointed towards me. It's actually the zombie's velocity vector. And also keep in mind that it has length equal to the speed of the zombie, because we're going to use that to our advantage in just a second. Okay? So now, the zombie's velocity vector is supposed to be pointing at me at position A, just as I said. So this is the zombie's velocity vector right here. And so that says this thing, x prime for the zombie, y prime for the zombie, points at x of a, y of a. Okay, so I now have one vector that's pointed straight at me, and that's the zombie's velocity vector. Now there's a second vector that's pointed straight at me. If I just take the coordinates that I have, xa, ya, and I subtract the coordinates that the zombie has, that will give me the vector za. And that is a vector that points straight at me, because it is, in fact, the vector that starts at the zombie's position and ends at my position. So this is now a second vector that points straight at me at any given time from the zombie to me. All right? I want to try to get rid of the length of that vector. I don't like the length of that vector, so I'm going to divide that vector by its length, and that gives me what's called a unit vector pointed straight at me. Okay? And a unit vector just means that its length is 1. Whenever I divide a vector by its length, which is this here, I get a vector that has unit length 1. So now I've created a vector that points straight at me with unit length. Okay? So again, we're going to let sc be the speed of the zombie as we did before, and I'm going to multiply this vector by sc. And by doing that, I have created a vector that points at me. That was the unit vector that points at me. But I've manipulated its length to be the length of the velocity vector, because I multiplied it by the speed. That makes it the velocity vector. There is only one vector that points straight at me that also has length equal to the speed, and that is the velocity vector. So we've now created a vector that is the velocity vector right here. All right? Now, if I just write out what that means, the velocity vector was x prime of z, y prime of z, and over here I've got all this. Well, this can be unpacked. Okay, I can look at the x-coordinate and the y-coordinate of this, and when I do that, I get dx dt, that's the derivative up here, is equal to this expression, and dy dt is equal to this expression, just by looking at the two components of this vector and breaking it up into these two equations. And this is a pair of what are called coupled differential equations. Okay? So if we can solve this system of two differential equations, we can then figure out what the path of the zombie will be as it chases me along this circle. Now, the last thing I'm going to do here is, remember, we did figure out what x sub a and y sub a are. Those were my coordinates as I ran around the circle. So I'm going to add those into the top. I'm going to replace x sub a by r cosine omega t and y sub a by r sine omega t. They're messy, they're ugly, but these are the two equations that dictate the motion of that zombie as I'm riding in a circle on my bike, this way. I'm riding in a circle on the bike. Okay? Great. So all we have to do is solve these equations. That would be wonderful. Can't be done. Okay? Nobody has ever been able to solve these equations. These are very difficult, messy equations to solve. So you can't solve them. So what do? Instead, you just run a computer using these and see what the paths look like. Okay? So let's take a look and see what happens if you use these equations to govern the path of the zombie. So here's the first situation. The zombie's in red, and it's chasing me as I ride around on the bike. And you'll watch what happens. And it seems to be sort of coming in on that little dotted circle there, that red dotted circle. Okay? Let's try another one. So this time I started the zombie up here. I'm going to start the zombie down here this time. Still chasing me, still always trying to head straight towards me, using its velocity vector headed straight towards me. And once again, it seems to be circling in on that red circle. It's kind of interesting that it's doing that. And in fact, that will happen all the time, no matter where you start the zombie. The zombie will always have a path that slowly works its way in towards that red circle. If you started over here, it looks like this. If you started over here, it looks like this. That happens again and again and again. That circle is called the limit cycle. Okay? So that's the limit cycle. And you're finding the zombies are always ending up nearer and nearer to the limit cycle. If you start a zombie right on the limit cycle, as we have right here, and you know that its tangent vector is starting out pointing at me right at the start, and then you let it go, what happens is this. It actually follows me around the whole way around, always stays exactly the same distance from me all the way around that circle, and ends up in the same place that it started at if I end up where I started. Okay? So it just stays right there the whole time. So what's happening is its tangent vector is always pointed, its velocity vector is always pointed straight at me, and as we go around, it just stays pointed straight at me all the way around. Never varies, always pointed in the same direction as we go around there. Okay? So what happens if we start with a bunch of zombies all following me? Well, notice what they do. Guy almost caught me there. And you'll notice they bunch. They bunch on that limit cycle. Okay? So they all bunch up and they all do this, and it doesn't matter where they start. The only assumption I'm making, which I didn't mention before, but the only assumption I'm making is that all the zombies are traveling at the same speed. Okay? So the zombies are traveling at the same speed, but if they do that, they will bunch just like this. Now you can use that to your advantage, as for instance occurred in this particular situation that again occurred on the Williams campus. These are two students trying to escape. So I'm going to ride my bike and see if I can help them. So let's see what we can do here. Of course, safety first. Put the helmet on. All right, I'm going to try to attract the zombies to me. Here we go. Wish me luck. Let's see what happens. All right, you zombies. Hey, follow me. Come on, you zombies. Follow me over here. Come on, you're not so smart anymore. You used to be academics. You're not anymore, are you? That's good. Good zombies. Come on. Working like a charm. Nothing like an afternoon bike ride with a bunch of zombies behind you in a pack. I'm riding in a big circle around the quad right now. See, notice they're starting to follow me. They're starting to group together. And the idea is that the zombies are always going to head towards where I am. And what that means is their tangent vectors are always pointed straight at me. Now, because of that, it turns out that no matter where they start, they end up actually grouping in a clump, and they end up following me on a circle that has a smaller radius than my circle. So my circle's bigger than theirs because I'm riding faster than they're moving. But I end up getting all of them to follow me. So eventually, they'll be all together, in which case these people can escape. All right, the zombies are following me. Okay, you folks, I think you're clear. You can get out of there and get to safety as quickly as possible. All right, looks like they're good. Now I just got to get to safety. So hang on just a second. I'm going to bring it around. Come on, you zombies. So there you get the idea. So you could actually use this to your advantage if you know the fact that these zombies are going to follow you in a circle and they're going to clump together. That's a huge advantage. Now I want to talk a little bit about the long-term prognosis. Okay, so this has been a few years now since this whole thing started. We've survived this far, but how long will this go on? So first, let's let h of t be the number of humans at any given time. Let's let z of t be the number of zombies at any given time. Let's let dh dt be the rate of change in the number of humans, and let dz dt be the rate of change in the number of zombies. And let's first think about what happened initially. Initially, for the zombies, there was unlimited resources, and those resources were us. Okay, so they had plenty to eat, they had plenty of people to convert into zombies, and so there was this immense growth in the number of zombies, and that was exponential growth that you see right here. So that's exponential growth. Initially, when the initial moments of infection occurred, we saw exponential growth in the number of zombies. Okay? But that couldn't be sustained forever, because eventually the number of people that are out there starts to drop. The number of zombies grows and the number of people drops. And so eventually you find yourself in a case of logistic growth. And this is a case of logistic growth where you can think of this as the rate of change in the number of zombies will be proportional to the number of zombies times the number of people left who have not been killed or turned into zombies. Okay? So we're losing a lot of people here. This is still proportional to this, because this is really keeping track of the number of interactions that there are between zombies and people. If there's very few people left, then there's not going to be a lot of interactions. If there's very few zombies, there won't be a lot of interactions. So when either of these two terms get small, there won't be a lot of interactions. If both of these terms are reasonably big, you'll get more interactions, you'll get more people turning into zombies, and the growth in the number of zombies will continue. If I multiply that out and then think about what's going on, here's the curve that comes from that so-called logistic growth curve. And you'll notice this first term, when z is small, this term is a lot bigger than this one, because z squared is going to be smaller than z. So this is a big term. And this is actually exponential growth. So that's the growth that you saw initially is right here. That's the exponential growth you see in the beginning. But then it tails off because of this term right here. And in fact, you can see it better on this one. As soon as p0 minus z gets small, dz dt is going to go to 0, which means this thing has to flatten out. It has to go to have a derivative of 0, which means getting closer and closer to a derivative of 0, which means it's going to tail off with time. Okay? So that's the medium long term. But now I want to talk about the really long term. Sorry, this is the equation that you get from that logarithmic growth. And so that's logistic growth. Okay? Logistic growth. Okay, so now I want to talk about the greater long-term situation. So this is very long-term. And it turns out that these two differential equations that give me the rate of change of the number of humans and the rate of change of the number of zombies govern what's going to happen. And so this first term, I want you to think about, if there were no zombies whatsoever and humans had lots of resources, then in fact the rate of growth of the number of humans is just going to be proportional to the number of humans. Humans have a tendency to breed, and as they breed they create more humans. Okay? So that's what that term represents. But of course, there is interaction between humans and zombies once zombies are around. And every time there's a human-zombie interaction, not in every case, but often in those cases, we lose some humans each time that happens, which is why we have this minus beta times capital H times capital Z. So that's the rate of change in the number of humans. For the rate of change in the number of zombies, if there are no humans around, the number of zombies will drop. And the reason the number of zombies is going to drop is because, as we said before, they have to have sustenance in order to survive. They do starve to death. Zombies can starve to death, unlike what a lot of people assume. And so you will lose zombies if there's no humans. But every time there's a human-zombie interaction, that can increase the number of zombies. And so that's why we have this term right here. Okay? So these two equations are supposed to govern what happens to the number of humans and the number of zombies. All right, so let's look at those two equations. And I'm going to factor a capital H out of the top one. I'm going to factor a capital Z out of the bottom one. And then let's look at the critical points. Critical points is where the rate of change of the number of humans and the rate of change of the number of zombies is 0. Those numbers are not changing. So those critical points are going to correspond to solutions of this. And there's two possibilities. You could have both H and Z be 0. That would certainly make this true. And you can have H equal gamma over delta, which would make this 0, and Z equals alpha over beta, which would make this 0. So those are two possibilities for so-called critical points where we would be in stable populations. Let's talk about the first one. When H and Z equals 0, it is definitely true that the rate of change of the number of humans and the rate of change of the number of zombies are both 0. The good news is the zombies are all dead. The bad news is we're dead too. Okay? So that's not a great situation. So we don't really want to be in that situation. So we'd like to analyze what happens in the other situations. So I'm going to use this fact that by the chain rule I can write dz dt in this way, and then I'll divide through, and I'm going to look at what is the rate of change of the number of zombies depending on the number of humans. Okay? And I'll get that by taking the equation I had for dz dt and dividing it by the equation I had for dh dt. So I get an expression that looks like this. Okay? And I'm now going to look at that in the ZH plane. Okay, so each point in the ZH plane will correspond to a particular number of humans and a particular number of zombies. And this will correspond to a slope. And so I'm going to draw those slopes, what's called a slope field, in the HZ plane. So H is on this axis down here. Z is on this axis over here. You remember that critical point, which was Z equals alpha over beta, H equals gamma over delta. That's this point right at the center. But at these other points, I can have horizontal slopes here. That's when dz dt equals 0 all the way along there. Over here, I have vertical slopes. That's when dh dt was 0, and so dz over dh will be infinity. Okay? And then I can also draw some other slopes. And this slope field exists, and from that slope field I can create solution curves that just touch. These are the tangent lines to the solution curves, and they look something like this. And so we want to think about what happens if we start on one of these solution curves, and we're just going to travel around it, okay, as the number of humans and the number of zombies varies. So we're going to start at a point over here. And so here's the situation. And this was the situation we started in. In this situation, initially, when the whole zombie infection started, there were very few zombies and there were a lot of humans. Okay, so we were right here. And then what happened was the number of zombies started to increase very fast. So the zombies went up very fast. And as the number of zombies went up, the number of humans started to go down. As the zombies increased in number, then the humans started to drop. And we found ourselves in a position like this. Okay, lots of zombies, very few humans. Then, because the zombies had nothing to eat, the number of zombies started to drop. They started to starve to death, and they didn't have anyone to convert to become zombies, and so this thing started dropping down here, and we found ourselves in a situation where the number of zombies and the number of humans was low. Now, in that situation, because there were so few zombies, the human race had a chance to recover, had a chance to procreate, and the numbers started to grow back again, and this is where we are today. We're back here at the point that we started at, where there are very few zombies, but very many humans. Now, of course, the zombies are poised to make a comeback because there's humans to eat and humans to convert, and we're going to find ourselves going around this path again and again and again. So we find ourselves in a situation, the cyclic situation, where the number of humans is large and then it drops down low, the number of zombies is large and then it drops down, and we just keep going again and again and again like that. Now, of course, this is the case that we care about the most, but there are other situations where this occurs. A very famous case is on Isle Royale National Park, which is in Lake Superior. This is a national park in Lake Superior. And that island had been colonized by moose. And the moose had lived there for a long time, and there were on the order of 2,500 moose on that island, when one day 2 wolves swam across to the island and established their own little colony on the island, and they started eating the moose. And so the moose population suddenly dropped. And as the moose population dropped, the wolves were thriving until the moose population got too low, at which point the wolves started starving to death. And so then the moose had a chance to recover, which they did, and then the wolves had a chance to recover. And this cyclic property, these so-called predator-prey models, occurred actually in this particular situation. They've been keeping track of the number of wolves and the number of moose now for close to 100 years, I believe it is. And they see this cyclic behavior that occurs right there. So it's not just for zombies that this occurs. So anyway, we're going to be trapped in this situation of this cyclic relationship between the number of zombies and the number of humans for who knows how long, unless we can be smart. And that's the trick. So I'm just going to end with a couple of credits here. But keep in mind, just try to be clever and then use the zombies' lack of intelligence to your advantage.
Wishing you harm. You see, I try to hold your hand, but I'm missing an arm. And brains are all I've eaten all week, it's true. But if my heart was still beating, it would beat for you. So let me take you to Wendy's, you deserve it. Yeah, I'm a zombie, baby, ain't nobody perfect. I'll chase you through the yard and all through the house.
So thank you very much for listening. I really appreciate you coming and listening. Thank you. Thank you very much. Thank you. And I would be happy to take any questions or comments or suggestions for how to survive the zombie apocalypse. Anything's useful? Yeah, please.
So I had a key question. You're talking about the zombies as opposed in relation to the wolves and moose on Isle Royale National Park.
Yes.
And you had that point where the 2 wolves swim across.
Yes.
And I assume there was a similar thing with when the zombies started destroying us all. Whether it was a research monkey in a lab that got out in 28 days later or whatever that. Is there a way to integrate some of that into mathematics of like, here's the unknown that may come in, and here's like the unknown that may come in and actually destroy that the loop you drew at the end?
So, I mean, once the loop gets established, as in the case of the wolves, as in the case of the zombies, in the case of the zombies, it was a lab at Harvard where they were experimenting. They did some things they shouldn't have done. But once it's established, then that loop can continue unless you can come up with something else. But maybe you're suggesting doing something else to disrupt the loop? Is that what you mean?
Super zombies.
Now
because, that would have to, they would eat the zombies then. And then you would have predator, prey interacting. And I wonder that would create a more complex loop.
Sometimes when you try things like that, you regret it later.
Super duper zombies.
Actually, that's an even better idea. Yeah, I mean, maybe it would work. I don't know, but there is some risk involved in creating super zombies, I think. And the other thing is that zombies have an evolutionary avoidance of eating each other. That's one of the things. And so, if you're going to come up with a super zombie, it might be difficult to do because that's to their evolutionary advantage not to eat each other, which is in fact the reason that these viruses that infect them don't allow them to do so. That's my understanding of the technical questions. Yes.
Thank you.
Yeah. Other questions or comments? Yeah.
So what happens to people who don't pass calculus?
They're all gone now, actually. It's very sad, but they're mostly gone. Yeah, no, it's
I'm trying to tell my kids that. So
yes.
Thank you.
Yes. No, that's right. No, that's the hope, is that people will take this to heart and learn calculus so that they'll be safe in a situation like this. Yeah. There's some interesting questions, actually, that come up. Here's one that somebody asked me when I gave this talk a couple of weeks ago, actually, and I think it's an interesting question. So we know what happens when you take a circle and you ride in a circle and the zombie's heading straight for you. And we know what the path of the zombie does. It moves in on that perfect circle limit cycle. What if you're on an ellipse? Just change it a little bit, okay? So instead of being on a circle, you're on an ellipse. You sort of squashed it down a little bit. You're going around the ellipse. The hard part is it's even hard to figure out what the parameterization of an ellipse is if you're going at a constant speed. That's not so easy to even figure out. But let's say you're doing that. So you're going on a constant speed. You're on your bike, but you're riding in an ellipse. What path does the zombie take? Is there even a limit cycle? I don't even know the answer to that, quite honestly. It's not even clear that there is a limit cycle, and if there is, what is that limit cycle? What does it look like? And it's kind of interesting because when you play around with it, you can see that it does some very weird things. And so there's a lot of kind of questions like that nobody's ever thought about, I don't think, as far as I know. So, the mathematics of zombie pursuit. It's a whole new field. Yeah. Yeah.
So, kind of a not a higher level question, but some of the references you made to like the math gene by Dean Devlin. I think you wrote a book about the idea that mathematics are innate, or in the case of the dog that would go catch the ball. And so I know there's been a lot of research about this, and some people have been talking about whether the idea of we're actually doing those equations in our head natively, or just something that we've actually evolved or whatever that actually does it. But in the case of your example of the zombies, why they move in straight lines, which makes all this possible, what part of that brain do you think would actually be a thing that was actually destroyed that prevents them? Like you go from the mammalian to the reptile brain.
Yeah.
The dog has a mammal brain, so it's able to actually do the.
Well, I mean, it's really interesting because although it's true that Elvis is smart enough, Elvis is a really smart dog. I should say Elvis was a really smart dog. Elvis passed away last summer. It was very sad. But Elvis was a really smart dog, and dogs, when they chase a rabbit, do not try to cut off the rabbit. They always head for straight where the rabbit is, in fact. So in fact, the vast majority of dogs don't know that they should try to cut off. And it's trickier with a rabbit, I guess, because if you head to where the rabbit is going to be, the rabbit often goes the other direction. The rabbit is smart enough to then head in a separate direction, so the rabbit's not going in a straight line path. But dogs tend to head for where the animal is, and most animals, when they're hunting, will do that. They won't cut off the animal. They will head for where the animal is at that particular instant.
Have you seen Jurassic Park and the velociraptors that they lie to me? I'm so excited. Go ahead.
Yeah. Yeah.
So can math provide hope for a professor that's slower than the professor that actually made it to the center? Because if zombies are just generally faster than you.
Yes. Yeah, so certainly one of the things that we talk about in the book is the fact that if you think of the various speeds that people have as a bell curve, as a normal distribution, that there are certain ones, and so one of the characters argues that we shouldn't try to help these people who are down at this end of the bell curve because they don't have a chance. That if you're moving slower than the zombie, then you're in trouble. And I think that's true. I don't know, like there's no curve that you can create that will protect you if you are slower than the zombie, right? Eventually the zombie will catch you. So you're kind of stuck, and especially because if the zombie's heading straight for you. If the zombie was doing something else, you might be able to figure out something. Like suppose the zombie was always heading for where you were, you could maybe turn around and go the opposite direction, and before the zombie realized it, you could sort of make it longer for it to actually, yeah. But in general, no solution for that. I'm afraid that group, mostly gone by now, unfortunately. Yeah, no, that's true.
We have a couple questions online.
Okay.
One of them is do you know the history of the word zombie?
I don't know the history of the word zombie. It's very interesting because I've gotten a little bit of flack because I picked a particular model for zombies, which is not necessarily the standard model. You know, the standard model is they are the walking dead, and they don't need sustenance, and they essentially live forever until their bodies decay away. And I needed this model because I wanted to be able to do predator-prey models, and I wanted to be able to have them starve to death. And so I needed, for my equations to be able to work, I needed this particular model. But some zombie aficionados are very unhappy about that. So I obviously am not as knowledgeable about zombies as some of the other people who are out there who take it very seriously, as it turns out. Yeah, yeah.
The other question was around, let's see, so we were having a little argument around, he says, when I'm under attack by a zombie, how will I have time to stop and make these calculations? There's some simple tool that will help me figure it out on the run, and so I suggested he study ahead, study up now.
I think somebody's got to create an app, right?
There you go.
Yeah, somebody's got to create an app that's to protect yourself.
I'm not going to remember unless I'm constantly doing it. It's just not practical to practice it every day. Do you have any suggestions for what to do when the apocalypse hits, other than studying calculus books?
Well, I mean, obviously my recommendation is studying calculus, right? And if you can keep yourself alive long enough while you're studying calculus, it will be to your advantage, definitely. But beyond that, I mean, there are various things that people say. For instance, they say move into the second floor of your house and then destroy the staircase. Okay, and I think that's true because zombies can't climb. Or else, in the book, actually, I have the characters actually move up to Canada because it turns out that cold temperature causes the zombies to hibernate because they did devolve into this earlier evolutionary state. And then that allows me to do Newton's law of cooling. So of course I manipulate things to do the things I want to do. And what they do is they move up to Canada and they build tree houses. And they live in tree houses up in Canada where the zombies can't get them and where they can pull up the rope ladder. And at night they're safe. And so yeah, so little things like that, I think, that you have to use to your advantage. Yeah. Yes?
Is it coincidence that you mentioned a reptile brain? I mean, that's sort of scientifically not accurate, but it's a widely read book among trial lawyers.
Is that right?
Yeah, it's called The Reptile. And it's that you want to pick a jury and then make your trial arguments based on the fact that you're appealing to the reptile, the alleged reptile portion of the brain.
Oh, interesting.
And you used it as just the way you stated it is very similar language.
Yeah, yeah.
But it's not true at all.
It's not true at all that there is an underlying earlier. See, I still believe, I mean, you can tell me that I'm wrong, but I still believe that we did evolve from animals of a much different type, and there's probably some portions of our brain that came from that, right? I've always loved that idea, but you don't like it. No, I think, I mean, right? I mean, I'm shocked by how similar my thought processes are to my dog's. I'm shocked by that. I'm shocked by how smart my dog is and how the relationship that we have and the fact that we can have all that. And I am convinced that that's because we evolved from similar animals. And so my guess is that there really is some stuff that's left over from some point that formed the basis of what became human, although it might not be a reptile necessarily. But
you get a call from any trial lawyers, it's
I can consult. I'll make a fortune. Yeah, it'd be great. Yeah.
All right, well, we have time for one more if anyone has one. Otherwise, Colin, thank you so much.
Okay, thank you. Thanks for coming, everybody. Thank you.